It gives me great pleasure to welcome you all to this online workshop on GEM5 Computer Architecture Simulation Tool, organized as part of the course PBCST 404 Computer Organization and Architecture. We are honored to have with us today our esteemed resource person, Dr. Manju R., Associate Professor, Department of Information Technology, GEC Barton Hill, Trivandrum. Dr. Manju R. is an expert researcher in the field of computer architecture, and her extensive experience in both teaching and research makes her an ideal mentor for this workshop. Her insight into this architectural simulation tools like GEM5 will greatly help our students to bridge the gap between theoretical concept and practical implementation. With great pleasure, I take this opportunity to warmly welcome Manju ma'am. I would also like to extend a warm welcome to all the faculty members and students who have joined us today. Once again, I extend a warm and hearty welcome to Dr. Manju R. And we thank her for taking the time to share her knowledge with us. Thank you, and over to you, ma'am.
Thank you, ma'am, for the introduction. A very good evening to all of you. First of all, I would like to thank Vimal Jodi for inviting me for this session. And yeah, so without any introduction, I think I'll just start the session. And to start with, I just wanted to add one thing. I'm not a person who actually likes taking sessions through online, especially for GEM5, because what I feel is I should have direct interaction with students as well as faculty whenever I teach these kind of things. But then, due to some unavoidable reasons, this is the only option. So what I will do is for the next 2 days, our plan will be I'll give a glimpse of GEM5. I won't say that I will be giving you the whole structure, and I'm not sure whether, because this is just kind of like a one-way session kind of thing. I'm not sure whether you will be getting it or not. So if you have any questions in between, I would be happy to answer it, and whatever I know, I'll definitely share with you guys. So to start with, my plan is today I will give you an introduction to GEM5, like why you should go for a tool like GEM5, and then we'll start some concepts in GEM5 and a walkthrough through GEM5 maybe, like that is my plan. And tomorrow, like we can actually have some experiments kind of thing. It depends upon your interest onto that. So tomorrow we will be doing some or we'll be showing you some experiments, how to start with GEM5, what are the things which you have to look into, and all those stuffs. So that's my plan. Okay. To start with, is my screen visible to all of you?
Yes, ma'am, it is
Yes, ma'am.
visible.
Yeah. Yeah. So the topic which we will be discussing today is, of course, GEM5 simulator. So to start with, before going to the GEM5 simulator, you should know why you should actually work with GEM5 simulator as such, because why it has been introduced onto your syllabus. So in that case, what you can look into is see, if you're a person at the end of the day, if you got a job in some system architect or an semiconductor industry, so your aim will be you have to work with either processor, cache, or memory. And I'm sure, ma'am, these students are from S4, right? Jasmine, ma'am, is the students are from, or anyone can actually answer me. You are from S4, right?
Yes, ma'am. Yes, ma'am.
Yeah, so you must have heard about processor, cache, main memory, and everything, right? So basically, what happens is whenever you have some, what do you say, modifications to be done onto your system. Suppose you wanted to actually invent a new chip by yourself, or you are working with a group who is actually inventing a new chip. So Okay, so there you have to either work with the processor part, or you have to work with the cache part, or sometimes you have to work with the memory part. So in this case, how will you actually tell the person, like the group, that you have, suppose you have actually made a new module for the processor. So how will you actually validate that new module to the community as well as to the group? Okay, so in that case, you need some architectural simulators. Like you have to actually work with some simulators where you can actually show what you wanted to. Because at the end of the day, whatever you will be saying, that will be a hardware part, right? You can't actually show that as a physical module and say that, hey, this component I can integrate with the processor and it is working. You can't say that. So of course you need some simulators where you can actually show the actual simulation which is similar to that of what is actually happening in semiconductor industry. So there comes the role of these kind of architectural simulators. Okay, so the ultimate aim of these simulators are to create a prototype of the idea which you are having. Suppose you are planning to create a new cash replacement policy. So the idea will be like, you will tell your group that I got a new replacement policy with me. So what you will do is, like, instead of creating the hardware circuit for that, you will actually create a prototype, and then you will show that to the industry or the academia, and then you will say that this is actually working correct. So in order to validate that, you need a simulator. So one such simulator is GEM5. And why GEM5 is actually, so what do you say, like famous in architectural or research, because of the code quality, modularity, and flexibility. So by saying that, I should say that when you say code quality, that is like, or modularity, it is something similar to like you are writing a program. So if you have written a program in C without actually, differentiating the functions as such, so when you want to make some changes onto any of the functions, it will be very difficult. But in GEM5 kind of simulators, the advantage is like, even if you want to work only with cache part, you can actually concentrate on that part only. If you want to concentrate only on processor part, I don't want to work with cache, or I don't want to work with anything else, you can actually concentrate on to one such folder, and you don't have to worry about rest of the processor architectures. So that is the advantage of GEM5. And and another thing is like, it's flexible in the case of the different set of CPU models actually it supports. So when I say CPU models, you must be knowing about RISC and CISC architectures kind of thing. So that you must have heard in your computer architecture class. Like the processor, the instruction set architecture will be different. So suppose you want to work with a CISC architecture. So how will I do that in GEM5? So the GEM5 actually provides a set of CPU models which are actually related with CISC, and there are also models which are related to CISC as well, RISC as well. And it is actually a mod object oriented design, means everything is actually, whatever you will see in GEM5, that is actually considered as objects. That is, everything is actually considered as set of events. Like, when if you like in general, you can actually see that as like when you click on your mouse, and actually there is an event happening there, right? So based upon that, something is happening in your system, right? So everything is actually being forwarded, or it is being executed based upon the events given by the user. So in GEM5, it is something similar to that is happening. And that is why it called an event driven simulators. And moving on to GEM5, how it is actually being invented, it is actually a combination of two simulators, GEMS and M5 simulators. And GEMS was a simulator which was actually invented by University of Michigan, and M5 is invented by University of Wisconsin. So GEMS basically it deals with whatever I was saying about the CPU models, ISAs, IO devices, and infrastructures, but they were not giving much importance to complex memory models or interconnect models. So we will be seeing what do you mean by these complex memory models, interconnect models, and what are the CPU models, and all those things in the in the upcoming slides. But the idea is like you there was two simulators, and one simulator was giving more importance to instruction set architectures, and other simulator was giving more importance to how the memory communications are being happening. So at the end of the day, they just wanted to create that into one single simulator so that you can simulate all the operations of your processor in a single simulator. And the advantage is that is this GEM5 simulator is a simulator that is widely used in industry till date. Even in AMD, Intel, you can see people who are working with GEM5 simulators to create their prototype and to communicate that with their managers and everyone. And talking about how it is being implemented, most of the implemented in CPP, and it is there is a wrapper for that. Like all the operations are finally controlled by Python. So it's kind of like you should have some idea about the basic CPP coding kind of thing. And the wrapper of that is like all the operations of CP, all the operations which you will be defining in GEM5, that is actually controlled with Python modules. That is how GEM5 simulators actually work. And why it is become popular in industry, because GEM5, the ultimate aim is to create a prototype of what is actually you wanted to convey to your industry or to academia. So suppose you want to create a, like I said, you want to create a new cash replacement policy, and you worked with that, and you actually created, you have coded that, its implementation, and you worked and you got the output. If you are showing the output using GEM5 tool, it is something similar to that. Like you can say that it is something similar to you have actually tested, like more or like you have tested that in a processor. So that's the importance of the output or the results which you are getting from GEM5. So with respect, so you must be knowing about, I'm not sure whether you know RTL, Register Transfer Language. At the end of the day, whatever commands you are giving to the processor, that is actually converted into assembly code. And at the end of the day, that is when it comes to either what do you say, onto the chip level, the language we will be saying it as called register transfer language. And if you can actually code your implementation, your cache replacement policy, or your anything which you want to work in the processor, if you're actually coding it using RTL, that is the best option. But coding in RTL is not that easy. But there comes the role of GEM5, where you can actually generate the same output which you will be getting something similar to that your RTL implementation. That's why accuracy wise, GEM5 is kind of like accuracy as well as flexibility wise. You can see that GEM5 plays a key role in semiconductor industry. So this is the system level view of GEM5. Like I can say that this keeps changing, and the number of CPU model it supports changes. But this is kind of like gives an intro to GEM5. So basically, in your CPU model, they will be concentrating on ISA and the model type. So when I say ISA, GEM5 actually support the two types of ISAs, like RISC and CISC ISAs. And also you will be able to, if you want to simulate interrupts, or if you want to simulate faults, or if you want to simulate transition look-aside buffer, where that is actually kind of a cache memory, where you can convert your, like transition look-aside buffer, you can go through it. Our aim or our importance is will be on the model type. So yeah, GEM5 actually what happens here is like it support different types of CPUs. One such CPU is, 1 minute, okay. Yeah. So the CPU models it supports is like atomic symbol CPU, timing symbol CPU, and in order and out of order CPU. So atomic symbol CPU means if you have an like an interconnection or like communication between your system and the memory, like this kind of thing, it will not give importance to whatever is happening or whatever communication is happening between the memory and your model or and your CPU. So basically, you can just simulate the basic communication, but it is not much importance to the communication between the CPU and the memory. So if you want a bit of more that such kind of communications, you can go for a model called timing symbol model, where it will wait or it will actually mimic the communication between CPU and the memory to some extent. The original implementation of whatever processor we are seeing right now are covered in these two models, that are in order CPU model and out of order CPU models. So in order CPU model and out of order CPU, are you like, do you know what is the difference between an in order CPU model and out of order CPU model? Like I can just show an example like this. So you must not be able to understand this pipeline in detail, but then in general, on the right side, let me just zoom it. In general, on the right side, you can see a set of operations. So in order CPU means all these operations will be executed. Like if I just give 1, 2, 3, 4, 5, all the instruction executed in the order itself. So if there is any dependency between two instructions, for example, you can say that this is operation, and mul is like you are adding R1, means you are multiplying R1 and R2, and the result is stored in R3. In order to do the second operation, add operation, you need the result of R3. So it's kind of like you can't just do this particular operation until you complete this multiply operation. So if it is an in-order CPU, what happens is like it will wait until you get the result. You can't just go further. So, but in the case of an out-of-order CPU, what happens is like if you have some instructions which are depending on the previous instruction, it actually won't wait, rather it will take the next instruction and it will see. Meanwhile, if the value of this is getting, you got the result of that value, add will be done. But out of order and in order, what you have to keep in mind is like all the instructions coming will be like, suppose you have 5 instructions here. These 5 instructions will be coming in the same order and it will be executed in the same order and it will go out. In out of order CPU, all the instructions will come, but the instruction execution won't be in the same order. It will actually change, but at the end of the day, it will actually submit. Like once it starts saving, it will be saved in the correct order itself. So that is the difference between in order CPU and out of order CPU. So these kind of, suppose you want to work with these kind of in order CPU models or out of order CPU models, such kind of models are actually there in GEM5 and you can work with that. And regarding a classic memory and Ruby memory module, classic memory means I am not interested in any other things. For example, I'll just show you. Um, Let me just. So this is kind of like a like you must be knowing about different cache and everything. So this you can just consider this as a core where you have a 4 core and there is an I think you have studied about caches. I'm not sure. Like Jasmine ma'am, have they studied caches?
Yeah, yes, ma'am. We have just started the cache memory.
Okay. Okay. So you must be knowing why we require caches, right? So it's kind of like, suppose you wanted to access something from the memory, like the amount of time it requires to take it from the memory, for example, from your main memory, like you can see that in the bottom. So from the main memory, if you want to take something, it will take too much time. So what happens is like in every chip, for every processor, there will be multiple level of caches, and whatever you required, it will be saved as intermediate in intermediate caches. And depends upon your processor, this level of caches will differ. For example, if this is kind of like a three-level cache hierarchy kind of thing, where every core has a like its own private L1 cache, and there is an L2 cache, and after that is there is a shared L3 cache. So what happens is like if the core is asking for some data, it will first check in. If it is an instruction, it will first check in L1 I cache. If it is a data, if it will check in L1 D cache. If it is not there, it will be going to the L2 cache. And from there, if the data is not there, it will go to like L3 cache. It will be shared. And if it is not there L3 caches, it will be going to the main memory. So this is how it works. Okay. So what happens here is like, I am not, if the memory interaction, so whatever memory interaction I am saying is like, I am not interested about anything else, rather just, saving the data and getting the information. For that, I can go for classic data. Like I just send the data, like I just request for a data, I'm just taking the data. I'm not concerned about anything else. So that is what is called classic memory. So Ruby memory module means, I'll just show you an example. 1 minute. So Ruby, to understand Ruby memory module, what you have to suppose, this is the architecture which you are having. Okay. So here you can see that you have multiple core here. Like for example, how many cores are there? One, two, three, four, like more than 15 cores are there. And this core, like core on the top left, this wants to come, it actually required a data. Okay. And that data is there in this top right corner one core. Okay. So what happens is, suppose that data is shared by someone else. For example, in this core, the data is in this core. And so when this core is actually asking for the data, the original data is here in this with this guy. Actually, it was owned by this guy. It was actually being, modified by this guy. So what happens is, if this core has to get the modified actual data, it has to get this information from all of these people. This is called coherency. So, like whenever you access a data, you have to understand that, that where exactly the currently modified data resides. So those kind of informations won't be there in classic memory module. So if it will just give you an idea about the basic interaction between your CPU model and the cache or whatever memory you are saying. It is not, what do you say, like it is not concerned about the coherency part. When I say coherency, that means like if the data is being modified by some other core, he won't be giving importance if you are working with classic memory model. If you work with Ruby memory model, it will be giving importance to that as well. So that is the difference between the two memory models. And as I said, in GEM5, you can actually see two types of CPU models. They are in-order CPU models and out-of-order CPU model. And in-order CPU models, like what you have studied in your computer architecture, it implements a five-stage pipeline processor, where if you want, you can go through the different stages. You can see how the different stages of a five-stage pipeline processor works, like fetch, decode, execute, mem, write back, everything you can see. And accordingly, there is out of order CPUs as well. It is there. And it depends upon what processor model you are using, like CPU model you are using. It will be having different stages of pipeline. Some will have 7 stages of pipeline kind of thing. So these kind of models are there in GEM5. And this is like, I was like talking about the classic memory module and the Ruby memory module. And if you want, like the classic memory module was inherited from M5 simulator, and Ruby memory module was inherited from GEMS simulator kind of thing. So going to the so that gives you an overview about how theoretically how GEM5 looks like. So this system level view will should give you an idea how the actual the theoretical part of GEM5 looks like, because understanding this will makes your job easier when you walk through GEM5. Then, so this is the now I'm going to the folders in GEM5. Like these are certain folders which you will be seeing when you open your GEM5. So one is like the build, and after that you can see configs. You have and M5 out source systems and test files. So the build is like, as I said, GEM5, we will be using GEM5 to model a processor, right? So like you will be saying what type of CPU model you want, what ISA architecture you want to work with and everything. So once you specify all these things, it will be whatever. Suppose you are saying that I want to work with a CISC model, and the CPU I wanted to work is an in-order CPU model. So you will be specifying everything or in the terminal, and once you run it, it will create a processor model for you, and that will be saved in build file. Okay, and whatever configurations related to your processor, for example, you wanted to change the cache size, you wanted to change the L1 cache size, L2 cache size, or you wanted to change something related to the processor kind of thing. So all those informations you can actually see in certain files, you can see in configs folder. So I'll be showing you those things afterwards. And ext means like, in this scenario you won't be using it much much here in your means course. Ext is something similar to like, suppose you wanted to take some what do you say, like power consumption of your processor or energy consumption of your processor. You want to integrate a tool onto your GEM5 and evaluate how it works. Those kind of things can be done under the folder like ext. And M5 out is something of which should be interesting to you guys, because M5 out is the folder where you will be seeing the output. Like if you are modeling a processor, or if you are modeling a cache, and you have created a CISC architecture and a CPU model and everything, and you wanted to see how the parameters has been changed. So these things you can see in M5 out folder. And after that, you can have a source folder where you will be seeing like what I have told you here. I told you that it supports these many types of CPU models, these types of classic or Ruby memory model kind of thing. So all these, things are kept inside source folder, and where you will be seeing, you can work with whatever folder, like files which you want. Suppose you want to work with O3 CPU. You can directly go to the O3 CPU folder, and then you can open and you can see how the different stages of pipeline works and everything. And another one is system folder, where the basic bootloaders are actually being added on to the system folders. And test, you can see some examples which you can run when you start with GEM5. But then in your case, we will be creating our own benchmarks and everything, and we will be working with that. So this will give you an idea about some of the folders you must be familiar with. And to be precise, you have to concentrate on the configs folder, M5 folder, M5 out folder, and source folder. Like you have to give importance to these folders. Okay. And when you go to source folders, you can see that it will be some of the important folders in this one is like architecture folder, CPU folder, and mem folder. So architecture folder, in architecture folder, you can see the ISA supported by GEM5. Like, suppose you want to work with RISC-V processors, or you want to work with x86 processors. You can't just use GEM5 and go and there and see and say that, okay, now I'll just create a RISC-V implementation here. You can't do that. Until and unless GEM5 support that architecture, you can't do that. Fortunately, like GEM5 support most of the famous architectures, and we will be working mostly with x86 and RISC-V processors kind of thing. And and also you can under the CPU folder, like I said, you can see the different CPU models supported by GEM5, like Miner, O3. O3 here this O3 is the CPU model, that is the out of order CPU model. So processor or performance wise, out of order CPU is the best one. And in memory, you can see the two memory models I was talking about. So if you don't want to work with cache coherency, like how the data is being modified, whether the actual data is being received to the sender kind of thing, if you are not worried about these kind of things, you can concentrate on the cache folder kind of thing. Otherwise, if you are worried, or if you want to with the actual cache coherency problems, then you have to go to the Ruby folder. So these are the some of the important folders which you will be seeing in your GEM5 tool. And now going to building GEM5, this is how it works. So basically the command building GEM5 means this is the command you will be using. Okay, scons build the guest architecture GEM5 dot optimization level, you have to minus J, the number of cores in your machine. So this is how it works. So here build like after the, with this, what it does is like, I am just saying that I'm just giving you a tutorial where I'm saying that you create or you simulate an x86 processor, and the CPU model simulate an x86 processor. Okay, so that will be your first task. So in that case, you have to specify it like scon build slash. Here you will be specifying the architecture which you want to build. If you want to build RISC-V instead of x86, you will give RISC-V here. If you want to build x86, you will give x86 instead of this guest architecture. After that, slash, you will specify GEM5 dot optimization level. Optimization levels are, these are the three optimization level which we will be concentrating on. So optimization level is like when you build this architecture, how much debug information you require from this about the architecture which you build. For example, if you just require all the, like you don't require not much optimization information, all the debug symbols, you can go for debug. And if you want some optimizations to be done, you will be going for this one, OPT. And I'm not interested in debug symbols, I can go for fast. So these are the three levels, and the good thing or the optimal thing is you go for OPT. So you will get some debugging information. So like whenever you have some errors or something like that, you will get an idea how it works. So it's better when you build your architecture, build it in optimization level, like with GEM5.opt. So this is how you start building your architecture. So for example, this is something, this is an example for your build command. It is like scons build. Here alpha is the ISA which I am using, and slash gem5.opt. After that, I am giving minus J4. That is like the number of processors, like what do you say, the number of cores in your system. So this is kind of you, what you have to understand is like, I guess I am not sure whether any of you have built it at this stage. So if you just start building this for the first time, what happens is like depends upon your processor or your system spec, the time it requires will vary. So if you have a 5-core processor, or you have a 10-core processor system you have, then it will take time. Here, when I say minus J4 means you are dividing the building of GEM5 across the number of cores in your system. Okay, so that is what is happening here. So instead of giving minus J4, I'll show you how to give, because if you don't know how many cores your system has, you can give the command directly there. That I will show you. So this is how it works. Okay, so you will be giving scons build alpha gem5.obt, and after that you will specify the number of cores kind of thing. So once you do that, what happens is like it will take, depends upon your processor. It might take 30 minutes, it might take 15 minutes. So if it is like a high-end workstation kind of thing, it will get over in 15 minutes. But if it is a normal laptop or a desktop, mostly it will take 30 to 40 minutes, and sometimes your system will just blink for some time. You might think that it will get hang. No, it will. It sometimes it happens like that, but wait patiently, and after 30 to 40 minutes, if you get a message like this, XCons done building targets, that means whatever architecture which you wanted to create has been built. So for example, if I have given alpha, like the command is like this, what happens is like it created an alpha architecture, and the architecture is ready to be executed. Now we using that architecture, you can create your new cache replacement policy, or you can create modifications to the existing processor components. Whatever you want, you can do that. So that is the second part. So after this, what we will be doing is like we have to use this architecture to simulate the functionalities which you are actually talking about. For example, you are now like suppose your aim was to create a cache replacement policy, and you want to test that cache replacement policy in this architecture. So how will you simulate that? So to simulate that, you have to actually give an input to your architecture, right? So that there comes the role of like you have to give an input to the architecture. Like for example, suppose you have what do you say? Like I'm saying that you create a C program that performs sum of two numbers. So you must create a C program, and you're saying that, ma'am, I have completed the coding. So how will I test it, or how will you prove that your thing is working? You will be giving an input like 1 and 2, and if it gives 3, you will say that it works. And I'm also convinced with that. So whatever model which you create, at the end of the day, if you want to show that it's working, like the implementation which you have done is working, what you have to do is like you have to give an input to that tool, right? So that to that ISA. Okay, so that is what is going to do. So how will you give that input, and how will you simulate that? That can be done in two ways. Either you can go for a full system simulation, or you can go for a system emulation. So the difference between these two is like full system simulation means like I have a like the scenario where I am working is like I am simulating everything. For example, the operating system calls and everything, actual operating system will be loaded, and based upon that your ISA is going to work. And in the case of system call emulation, I don't want to work with the actual OS. Rather, I will simulate the OS calls. So that is the system emulation, call kind of thing. So we here what happens is like I'm not interested in what are the system calls generated for my processor to work. Rather, I want those system calls to be simulated so that I can concentrate on my actual simulation. So that is system call emulation. So now comes the role of how will you run your application, or how will you test your thing like the cache replacement policy which you have done. So in order to test that, you have to choose in which model you have to work with. Suppose you want to work with full system simulation. Instead of this sc.py, I will be using fs.py. Okay, that is a Python file that is available in GEM5. You can go through, you can actually see that how it works and everything. And normally in your case, we won't be working with full system simulation. Rather, we will be working with system emulation mode, where I am not worried about the operating system, calls and other things. And after that, I want to give the input to be tested. So that is this part. So you can give the input through command line. So that is why I use -c. So what is the input which you have to give? So see, the thing which you have to keep in mind is like at this part, you have created an architecture. Okay, that consists of the cache files and all the other files. And that architecture I have to test with an input. So what is the input I can give it here? Okay, so it's nothing like I can give sum of two numbers kind of a program here. It should be a program that will actually, you know, what do you say, like take all the capabilities of the processor which you have created. നമ്മൾ ഉണ്ടാക്കിയ ആ ഒരു പ്രോസസ്സറിന്റെ എല്ലാ കേപ്പബിലിറ്റീസും ടെസ്റ്റ് ചെയ്യുന്ന ഒരു ഇൻപുട്ട് ആയിരിക്കണം നമ്മൾ കൊടുക്കേണ്ടത്. So that is the part so that can be given through this part -c followed by this thing. Okay, so I will show you how this will be given and everything. So I'm just giving you an intro to everything. So this is how this works. So this is the system emulation call happens. This is how, like whenever you call sc.py, this is what is happening there. So whatever inputs you are giving, that is the bench or CFD kind of thing, that will be given for simulation. It depends upon, suppose you have multiple processor, you are simulating multiple core of your ISA, then it will be given to all those processors and the simulation will work. And if you want to work with the coherency, it will go to the Ruby memory module and it will start running. So this is how it actually looks when you call simulation sc.py file. And once you give this, you will get the output like this. Like you will be seeing like real simulation, entering event queue, starting simulation, increasing stack size by one page, like something similar to that you will be seeing. So if you get something like this, and remember one thing, when you do this, sometimes you will get some warnings. Sometimes you'll get so many messages in the command line. You don't have to worry about those things. Only one thing which you have to look is like whether it is exited successfully. Like you can see this line exiting at tick kind of thing. That means that actually exited without any errors. Otherwise, it will give with errors kind of thing. So if some errors are there, you can't see the output. So this is how it works. So basically, what we will be doing is like you will build the architecture which you want to work with, and after that, you will call the simulation mode in which you wanted to work with, and you will give the input to that. So once you do that, what you will get something like this in your output, and after that you can see the results. So where will you see the results? There comes the role of your M5 out. There in M5 out, you can see so many parameters and its results. Like you somebody's uh, yeah, Paul. Okay, yeah, okay. So so how will you see the output? So the output you can see in the folder M5 out. There is a folder. So whatever architecture which you have created, you have given to that architecture, you have given an input, and based upon that input, it created some changes onto your architecture. So you want to analyze what are the changes that are being made to your processor or the architecture. That you can see in the folder M5 out. There you will be seeing a stats.txt file. I will show you that, where you will be seeing some information like this. Okay. And this is kind of the interconnection networks, which you don't have to worry about right now. Like I won't be saying much about, like, this is basically, if you want to just give a glimpse about what is interconnection network, I'll just show you. So I was talking about this architecture, right? Here, if this core, there are so many cores are there. So if these core have to communicate with each other, they should have a link and they should have a network like the computer networks which we are studying. So like that, these guys has to communicate with each other. So for this communication, it will use a protocol. So that protocol is called the network on chip. Okay, and the model, like if you want to, work with that intercore communication kind of thing, you have to work with the Garnet model of GEM5. So that is all about the interconnection networks, and this is how it looks like. This is your core, and you will be seeing so many files related to your network on chip, and with which you can work with. You don't have to worry about this right now. And another one is like I was talking about like the inputs to your system. Okay, so the benchmarks. So whatever input you will be giving to your architecture, that is called, we call in research community, we call that as benchmarks. So benchmarks are like something which will test the performance of your architecture. Okay, so there are different types of benchmarks. One is called synthetic traffic benchmarks. It is like kind of simulate the actual communication happening in your core, in your processor. For example, if you just take this one, if it is a synthetic benchmark, it will just mimic the communication between different cores. There are different patterns. So depends upon the patterns of that communication which it is mimicking, you will be having different types of benchmarks. Synthetic traffic benchmark, that is called, it is synthetic traffic benchmarks. Okay, another one is called you don't have to worry about this now. So another one is called real workloads. So real workloads is like these are the set of inputs that are accepted by the industry. You can't just give test.c and run your architecture and say that, hey, my processor is giving good performance. You can't do that. So if the industry validate whatever you have created, if it is a cache memory or if it is a processor component which you are giving, so if you want to validate that, the input which is to be given to the processor, it should be an input that is accepted by the industry. So that kind of inputs are called real workloads. So one such workload is called the Standard Performance Evaluation Corporation Spec CPU 2006 benchmarks, where so it is called Spec CPU 2006 benchmarks. So it is something similar to a set of executables. That executables will be given to your architecture, and that will model different types of applications. For example, it is having executables of a multimedia application. It has executables of floating point operation. It has executables of integer operations, like that. So that is kind of it's so if you just look onto that, I would say that if my program is 100 lines, these kind of executables is kind of like millions of lines. So that is the difference. So you will be giving this to your architecture and test it. And using that, if the result is coming good, the industry will say that, okay, whatever you have created is good. So that is the relevance of real workloads. So this is how you will be working with real workloads. So this is how you will be working with real workload. But the problem with the real workloads is like that is not freely available to the academic community. So you have to purchase it, since like it was there in my lab. So that's why I was able to work with that. But then it is not available. So how will you create benchmarks by yourself, and how will you actually test your whatever mild things which you are creating right now? So I will be showing that after this session. Okay, so this will give you an overview about the overall components of GEM5 and those things. So if you have any doubts till this point, let me know. Otherwise, I'll just move to the GEM5 folder kind of thing, and how to create benchmarks and everything, I'll give you an idea. So any questions at this point, please let me know. Okay, I guess you don't
Students,
have any
if you
questions
have any
related
doubt,
to it.
please feel free to ask.
See, from my perspective, I should say that you should ask questions because otherwise, I'm not sure to what extent this is reaching you. But it will be difficult if you don't, understand the basics of whatever I'm saying right now. Uh, so if you have any questions, please ask me. Otherwise, I'll just show you the GEM5. Okay. So I guess it's better to go to the GEM5 folder. So let me just take the GEM5 folder. So this is like my like desktop is visible, right, ma'am?
Yes, it is visible, ma'am.
Yes, ma'am.
Okay, okay. So this is how your GEM5 looks like. GEM5 folder looks like. And whatever I was saying till this point, I was saying, talking about so many things. So this is the build file I was talking about. So what I have done here is like, you can just see, uh, 1 minute. So this see, can you just see the command which I have given here? I'm just trying to create an x86 architecture. So what I have done is like I have given scons build x86 slash gem5.opt. I was talking about -j, that will give you the number of cores you wanted to run this in your that number of cores available in your system. So if you don't know the number of cores, the command which will be used in Linux is called nproc. That will give you the idea about. You can directly call that command here. So if you just give like this, scons build x86 gem5.opt space -j $nproc, it will directly take the number of cores available in your system. And if you just press, this is how it works. So now for me, it won't take much time because I have already, built it beforehand. That's why it just, it will be completing in another 1 minute maybe. Sometimes remember when you do this, you can see that it is blinking like this. Just don't press enter or anything. You just wait until you get the next line. So once you get like this, so you can see here like scons done building target. That means I have created my x86 architecture. Okay. And now if I want to run something, it will be like this. Is it visible, ma'am? Like, or I'm not sure. Ma'am, is it visible? Like the command, is it visible?
Yes, ma'am. Ma'am,
Okay.
it is visible, ma'am.
Okay. So what happens is like, so what happens is here is like initially I have built it for the x86 architecture. Now I am going to run it. Okay. So how will I run it? So this is like the whatever OPT I created. So I am calling that build x86 gem5.opt. And after that, I have to call the sc.py file because I'm not interested in working with fs.py, right? So that is available in configs deprecated example folder. So I'll just show you. So in gem5, you go to configs. In the configs, you can see an, deprecated. In the configs, you will see deprecated one. In the deprecated, you can see example folder. There you will see two Python files, fs.py and sc.py. And if you just open it, it will look like this. You don't have to worry about the file because we are not planning to make any changes onto this. Rather, we will be using this to run our thing. Okay, so that's why it's like we will be calling that file. After that, you will be specifying the things which you require. Like one thing which you have to specify is the CPU model with which you want to work with. Here, what I'm doing is like I'm specifying that I want to work with x86 or 3 CPU. That is the out of order CPU that is there for x86 architecture. After that, I have to specify the input to be run on that particular CPU model. Then you if you want, you can specify the cache size and everything, like the L1D cache size which you want, L1I cache size which you want, everything, and the maximum number of instructions to be run. So that is what here what I have given is maximum number of instructions as 3. Okay, so what happens is like I have an input which is called uniform random. Okay, I'll show you what is this uniform random. So assume that is as actually as a program which you want to run in your system. Okay, so I'm just giving it through command prompt. So that is why I'm giving CMD uniform random, and I don't want that input to run for run till it gets completed. Rather, I wanted to run that for 1,000 instructions only. Okay, or 1,000 like 10,000 instructions only. How will you control it? You can control it using this one. Otherwise, depends upon your memory and processor spec. If you run without specifying max instructions, your system might get hanged. Okay, so it's better you start using max instructions and then run. So if you just give it like this and enter, you can see something like this. Okay, so you can see here exiting at tick 5078500 because a thread reached maximum instruction count. So the moment you see this one, you can be happy that your execution was okay. Like you have tested the input in your ISA using the CPU model, which you are specified. Okay, so that is the good thing. So now I have created the ISA, I have used the CPU model with which I wanted to work with, and I have given an input to that CPU model, and I have simulated it. Where will I see the result? For that, you have to go to GEM5, you go to M5 out, where you can see a file called stats.txt. You just open start.txt, you will be seeing so many variables related to your architecture. Some of them will be of importance to you, some might not be, kind of thing. It depends upon in which area you want to work with, kind of thing. For example, one parameter which most of us will be interested will be the parameter called CPI and IPC. So you must be knowing what is CPI and IPC, cycles per instruction, and IPC is cycle. So this will give you an idea about how good your system is, kind of thing. So basically, if the whatever model which you are saying is you implemented a new cache replacement policy. In terms of IPC, how will you say that the cache replacement policy is good? Only if the IPC is a higher value, like the number of instructions which you can execute per cycle is giving you a good value, then whatever you are proposing is good. But if whatever you are suggested was not a good method, if it is reducing IPC, that means it is not a good method. So this is how you will analyze the architecture or your implementation. Okay, so one such parameter is CPI or IPC. So you can see the value here. So what you can do is like you will have a base model where you won't be making any changes. You will note down the CPI and IPC, and after that, whatever you want to integrate onto GEM5, you will integrate. Then you will run. Then you will check what is the CPI and IPC value. If the IPC value is going high and CPI is going low, you can evaluate that as a good model. So this is in one way you will be assessing your processor. Okay. And another thing is, so this is how like you will run. So now the question is like, what is this input? How did I give this input? From where did I get this uniform random kind of thing? So here I told you like the input can be a synthetic benchmark or input can be a spec CPU real-time benchmarks. So synthetic benchmarks, unfortunately, only with coherency, like a Ruby memory model kind of thing. So that is not available for us. For classic memory models, you have to either use real benchmarks or you have to create benchmarks by yourself. So how will you create benchmarks by yourself? I'll just show you. So what I wanted to create here is like I wanted to create the benchmark uniform random. So to create that, what I have done here is like I have created a file called I have a uniform random.c file. So this is that C file. So my aim is like I wanted to mimic the memory access pattern. That is a uniformly like I am randomly accessing memory. Okay, so some access pattern. So I wanted to mimic that. So what I will do is like I will create a C program that will mimic the memory access pattern. That is kind of like you are randomly accessing memory of your system. So that is this C program. So this C program you can actually use chat GPT or whatever AI models which you are having. So you can create your the kind of benchmark which you wanted to give. Suppose I wanted to create a pattern access the memory sequentially. What you have to do is like create a C program that creates a memory access sequential, something similar to this. So once you have the C program, what you have to do is like you have to create an executable like this. So this we call this as your benchmark. So this executable will be the input to your GEM5, not the C program. Okay. So minus CMD equal to uniform random means I am giving this executable as input to my GEM5. So how will I create this GEM5 executable? For that, so this is your uniform random C. So what I will be doing that I have another access pattern called burst.c. So I will show you how to create executable for this burst.c. So what I have to do is like I will just open from this from here. Then I will just give the command like this: gcc minus o minus static minus o burst space burst.c. That is, I am creating an executable object file, and the name of that object file is burst. From where I'll be creating it? I'll be creating it from burst.c. Okay. And a static is like you can just go through it, like I don't want to have any connections kind of thing. And minus o is like the optimization level which you require. Okay. So what happens is like if you give minus O2 or O3 kind of thing, whatever assembly code it will generate will have all the optimizations in that. Suppose I don't want any optimizations to be added to my assembly code, I can just give that as minus O. Minus O 0. That means I'm not going for any optimization. So when you work with creating your, benchmark, you have to follow this, because if you just wanted to mimic data hazard or control hazard or structural hazard with this one, if optimization is there, it will be difficult. So that's why we will be giving that as minus 0. Okay. And then if you just enter, it will create an executable in the folder. Okay. So I have created the executable for burst. And what you have to do is like either you can give this path to your GEM5, or you can just copy that and go to the GEM5 folder. Inside the GEM5 folder, you just paste it. Okay. Now the executable is here. Now you can call that executable from your GEM5. From your GEM5, you can just call your executable. See, it worked. It worked with burst input. So this is how it works. So the first thing you can actually try out today is like you just try to create your own benchmark, some pattern. You can actually try straight pattern, or the same uniform random itself, or you can go for the burst pattern kind of thing. So create the pattern by yourself. Create, share the, what you say, the commands and everything today to Jasmine ma'am. Jasmine ma'am will be giving you that. So what you can do is like create your, your own benchmark, create the executable, add that onto your GEM5 if it is already installed, and then you try to execute and try to see which are getting GEM5 out, like here in the stats file. Depending upon the memory access patterns, these values will differ. So what you can do is like you can try different benchmark patterns. So what are the different CPI and IPC when you run burst? How that will be changed when you run uniform random, or if you run some other things. So you can try that and see yourself. Actually, you can add like 10,000 or 1 lakh. It depends upon that. It will take some time to complete. That's it. So it depends upon your system as well. So you can have you can give as many number of instructions you require. See, it got exited. So this is how it works. So that is one thing which I wanted to add. And another one which I wanted to show you is like yeah. So if you just wanted to work with, another, like the CPU model, which we were saying is like, okay, so how will I know that what are the different types of CPU models I have? So it'd be like, I have used x83 CPU models, but how will you know that how many CPU models are there? So that you can actually see by just giving minus minus hyphen CPU, minus minus CPU hyphen type, and then you give an enter. Here at the end, it will give you an error statement and it will show you what are the different CPU models available. Okay, so here you can see that there is atomic symbol CPU, there is minor CPU. Minor CPU is an in-order CPU. So if you want to work with an in-order CPU, you can go for x86 minor CPU. If you want to work with atomic symbol CPU kind of thing, you can go for that. So whatever CPU models, you can see it here. So you can actually explore giving different type of CPU models and check how the performance of the system changes by seeing the stats file. So that is another thing which you can do to start with. So these are the things. And yeah, so that is all about CPU models. And another thing is like, see, I wanted to change, like I was talking about the configs file, right? So what is the importance of this configs file? I'll just show you. So in configs file, like in that, if you go to the configs folder, you just go to the common. There is a folder called common where you just open options.py file, where you will be seeing the the like the parameters or the sizes of different components of your architecture. Suppose I wanted to work with a different L1 cache size or L1, everything you can the associativity, cache line size, and the number of directories, number of L2 caches with which you want to work with and everything. Because if you just see it here, I'm not specifying in this command, I'm not specifying any L1 cache size or L2 cache sizes or anything, right? But still it is working. That means it is taking the information from option.py. So whatever value I'm giving here, by default, these values will be taken and that will be loaded here and it will run. So if I just specify something like this, so if I just specify just like this, what happens is like whatever value you have given there, that will be over ride here, and it will be using this part. So this is how it works. So option.py also you can actually explore and see what are the different things which you can change and how it is being given and everything you can explore, and you will understand, okay, the parameters and all those stuffs. And another thing is like I was talking about, like in GEM5, another file I was talking about is like source file. As I told you, in source file, you can see, the two types of memory models that is available in mem folder. If you just click mem folder, you can see the Ruby folder is the one that is actually handling the, the coherency level kind of thing, which you don't want. So if you want to work with the classic memory model, you can just go to the cache folder. Okay, so you will be working in this folder, cache folder. So you can see the replacement policies associated with the cache, how the cache block is being created, and all the files you can see. And remember one thing, in GEM5, what happens is when compared with the normal CPP program, uh, like it is for every file there will be two files, like kind of thing, for every modules. There will be a CC file and there will be an HH file. So CC file is the one which will be talking about all the definitions of a particular implementation, and its declarations will be given in HH file. For example, if I just open this one, suppose I wanted to create a function called satisfy request. I can see that satisfy request here. Its definition, everything is defined here, but its declaration will be here in HH file. See, so its declaration will be defined in the HH file. So if you want to work with any files, always check its CC and HH file. So if you are planning to add any new functions onto your CC file, make sure that its declaration is in HH file and that will be called in CC file. Okay. So that is the another thing which you have to keep in mind. And the replacement policy. So if you are planning to work with cache kind of thing, you have to work only in this folder. You don't have to go anywhere else. And if you want to add a new replacement policy, you can just add it here. How to replacement policy onto the existing one and everything. Tomorrow we will actually cover and we will show you how to do that. And after that, if you just want to work with the cache block size or the basic things related to cache blocks, you can see that in cache.cc file kind of thing. So these are the files related to cache. That is why I was telling you GEM5 is what do you say, an object-oriented approach kind of thing, and it is modular as well, because see, you can clearly see that every classic memory related informations are here. You don't have to go anywhere else. It's here only. So if you want to work with Ruby memory module, you just go there. You don't have to worry about the rest of the things. So that is the beauty of GEM5. And so that gives you an idea about that part. And what else I would say here? Maybe, yeah, so this is like I told you, like if you want to work with coherency, like cache coherency, if you want to work with, you have to specify the coherency protocol with which you have to work with. Maybe I'll give you an idea about these things tomorrow. Like my students will be joining and they will be giving you an idea about what is this, like not in-depth knowledge about Messi 2 level or anything, but what is that all about and all those stuffs they will explain to you. And yeah, maybe by that, I guess, let me just check whether I can show something else. Yeah, so I'll just show you the different types of CPU models. This one, like I told you, all the CPU models are there in the folder called CPU. So you just click the CPU, you can see, like see, O3 CPU. So if you want to work with O3 CPU files, go to the O3 CPU file, you can see. See, you must have studied about fetch, decode, execute, and everything. You can see the files associated with that. Decode.cc, decode.i, it's HH file. You can see the fetch files as well. Like you can see it here. So the fetch informations are here. So if you want to work with in-order CPU, you just go to this minor folder. You just open the minor folder. You can see everything related to the in-order CPU, like the how the pipeline is being created. That if you want to give some prints and see, you can just give it in pipeline.c, and you will see how it works. If you want to know how the fetch operation works, you can just see it here, like fetch, this one, fetch.cc, HH file, CC file kind of thing. And if you want to work with execute.cc, you can see it here as well. So that is how it works. In you have CPU miner, and there are other CPU models as well. But then if you want to work with the simple CPU models kind of thing, you can go to the symbol folder kind of thing, like whatever I was saying, that atomic symbol CPU kind of things. You can go here. But I would suggest you should work with either O3 or minor folders. That will give you more idea about, because atomic symbol won't mimic the actual cache interactions and everything. So it's better to work with minor or O3 CPU kind of thing. So that will give you an idea. And the architectures which you can use in GEM5, I told you that it will be specified in arc file. So you can see that it accepts all these kind of things like RISC-V, Spark, x86, ARM, AMD GPU, MIPS, power, everything, like all the ISAs which have specified here, you can actually work with those things. And another thing which, let me just, yeah, this is the, like, these are some of the steps with which you can start exploring kind of thing. So for the time being, I will send the kind of, see, like the GEM5 which we are, GEM5, the problem with GEM5 is like in every month or in a month, maybe twice they will, release their versions. So whatever versions you will be downloading will be the one different from what we are using, because sometimes there will be problem with the compatibility of the, commands used in different versions. So to avoid that, we just want you guys to install the version which we are saying. So the instructions will be given by others. I guess others is in the others. Are you here?
Yes, ma'am.
Okay. Yeah, so my others will be, yeah, others will be giving he's my student, so he will be, giving you the, like the instructions to download the version with which you have to work on. So you just download that GEM5 version and follow the instructions others will be giving to you, and like install GEM5 by today itself, and try to before tomorrow's session, you just try to work with this executable, how to create the executable, how to run that executable, and you try to go through the M5 out and see how the stats.txt file looks like and everything. You can give it a try, and then you can come tomorrow, so that it will be easy, and all the files which I was talking about right now. Because tomorrow maybe like Adarsh and my other student Krishnan will be talking much about the cache and those stuffs. In that case, you have to have some idea about how these folders look like and everything. So we will be under the assumption that you will be completing all these things before tomorrow's session. Okay. So by that, I guess I'm just concluding today, and I'll share all the commands which I was showing you today, like these things to for you guys to try with. And to start with, I will do one thing. I'll just share this uniform random C file as well, and you can give it a try kind of thing. So yeah, that's it. So with this session, I know that you won't be getting much idea how to, like, you won't be getting whole idea how to start with GEM5, but this is the minimum thing which I can do in an online session to start with. So uh, try to, I can see that it is being recorded, so I would suggest you guys, go through whatever I am saying till this point of time, and try to explore, so that we can work with some real experiments, after 2 days maybe, or maybe in an offline session kind of thing. So it will be good for you only. So let's see. So by that, I just wanted to end my presentation for today. I hope I have given you some glimpses of GEM5, and if you have any doubts, you can contact me or others or my students. I'll share their numbers. You can talk to them and you can get an idea how to work and everything. And the numbers will be shared to Jasmine ma'am. Jasmine ma'am will share to you guys. So yeah, so by that, see you tomorrow. Thank you.
Hello, ma'am.
Yeah.
Hello, ma'am. Thank you, ma'am. Thank you so much
Yes,
for
yes, yes.
the insightful online session. The session was so
Yeah,
informative.
Jasmine.
Dear students, if you have any query, you just feel free to ask.
Or you can just send me a message to me or my students, but then make sure that you make use of this opportunity. Okay.
Yeah, sure,
Thank you,
ma'am.
Jasmine.
I will
So see
share.
you
I will
tomorrow. So
share the contact
tomorrow,
number.
yeah, yeah.
Ah,
Okay. So I'll just share the commands which I was showing you, now, and you can pass it to the students, and make sure that they are actually, they have tried it at least once before they join for the tomorrow session. Okay, Jasmine.
sure, ma'am. Ma'am, I do have a doubt.
Yeah.
Ah, while we are using WSL instead of a Linux system, if it is a Windows system,
Mm-hmm.
if you are using WSL, whether everything will be smooth like Linux system or something different.
Uh, like I have not used it using that, but then when we went to Muthoot, some of the students were using like that. Others, can you just പറ്റുമോ others അതില് എങ്ങനെയാ, will it create any problem?
മാം വർക്കാവും, ലൈക്ക് ബേസിക് കാര്യങ്ങൾ നമ്മൾ പഠിപ്പിക്കുന്ന റൺ ആവുന്നുണ്ടായിരുന്നു. ബട്ട് ഇൻഡെപ്ത് മറ്റേ ഫുൾ സിസ്റ്റം ഒന്നും വർക്കാവില്ല. SC മോഡ് വർക്കാവുന്നതാണ് വിശ്വാസം.
Okay.
ഓക്കെ, അങ്ങനെയാണെങ്കിൽ അത് വെച്ച് ട്രൈ ചെയ്യാം മാം. ഇപ്പൊ
Okay.
അവരോട് ഇപ്പം ലിനക്സ് ഇല്ലാന്നുണ്ടെങ്കിൽ അത് വെച്ച് ഒന്ന് ട്രൈ ചെയ്ത് നോക്കാൻ പറയാം. എന്തെങ്കിലും എറർ വരുവാണെങ്കിൽ വിൽ സി. ഓക്കെ.
ശരി മാം. ഷുവർ. ഓക്കെ മാം.
ഓക്കെ. അപ്പൊ ഞാൻ ഇതെല്ലാം ഞാനിപ്പോ ഞാനോ ആദർശം ഇപ്പം ജാസ്മിൻ ഇതെല്ലാം ഒന്ന് ഷെയർ ചെയ്തേക്കാം കേട്ടോ.
ഓക്കെ മാം.
ആ, ശരി ശരി. താങ്ക് യു.
Okay.
താങ്ക് യു
Thank
ഓൾ.
you. Thank you so much. Good
യാ,
night.
യാ. ബൈ. ഗുഡ് നൈറ്റ്. ഗുഡ് നൈറ്റ് ജാസ്മിൻ. ഗുഡ് നൈറ്റ്.
Students, you can leave now. Enter student.